Welcome to this OsmoDevCall tonight about a, fast forward to the future topic. We had a lot of old technologies in the 2G domain, TDM, E1, PDH, SIM card UART interfaces, and so on in the past. And now today we are talking about CUPS, control user plane separation, and the PFCP protocol, which is something that is much more modern than most of the things that we've covered here so far. So what is this about? It's about this relatively modern extension of the 3GPP architecture, which splits the control and the user plane in the evolved packet core. So the EPC evolved packet core is the acronym describing the 4G core network, consisting of the two basically 3-4 network elements, depending on what you want to look at. Here it's only about the packet data, so we're talking about the serving gateway, the SGW, and the packet gateway, PGW, and those are can be split if an implementation decides to go with this control user plane split. So the acronyms that we will see mostly here, of course there will be more, this is just the introductory acronyms. We have the serving gateway, which is the successor of the SGSN in the 4G network. So 2G, 3G had an SGSN. In 4G, it's the SGW. Also the PGW, which is the successor of the GGSN in the 4G network. And CUPS is the control user plane separation, the underlying principle of splitting those elements in a certain way. And PFCP, the packet forwarding control protocol, is a protocol used to communicate between CUPS-enabled network elements. So this is the slide that's missing. This was supposed to show a normal EPC with SGW and PGW. We'll skip over that. We assume that this is basically known, or at least if you know 2G, 3G, you know the SGSN and GGSN, and you can just basically look at this the same way. CUPS, as I said, is a relatively modern feature. It's from 3GPP release 14. It separates the serving gateway and packet gateway into control and user plane, as the name implies. We will see what that entails. It reminds me a lot of the much earlier split, 10 years earlier or even more, of splitting the MSC from a circuit switched MSC into an MSC and MSC server. Or media gateway and MSC server. That's actually a typo there, where originally in the circuit switch 2G networks, the MSC was handling both control and user plane. And then later on, they separated those two functions, or at least introduced the implementation option that the signaling side is running in one process, and the media gateway, the user plane handling, is running in another process. The same also is done, for example, in the Osmocom BSC implementation, where originally, very early on in OpenBSC, we handled both the user plane, meaning the voice data and voice audio mainly, and the signaling plane, control plane in the same process. And then later on, we introduced the media gateway that externalizes the user plane processing. And this is basically the same for the packet domain, where then there is a split. So the SGW is split into an SGWC and SGWU, so for control and user plane side, and the same for the PGW. This concept is described in 3GPP 23.214 in case somebody wants to look at more details of this principle. It defines the following architecture reference model. This is the diagram right off the spec that I just mentioned. So we have the serving gateway. This used to be one block here, basically, the control and user plane, and this is separated now with a new interface, the SXA interface between those two. And also the packet gateway gets split, where we have the control plane here and the user plane there. Ignore the TDF, that's an optional element that we don't care about here, that can just ignore that for the time being. So here on the left, further to the left, we have in 4G, we have the MME and the eNode B and so on, and the subscribers. And over here, we have the IP next to the SGI interface. We have the IP services, meaning internet, IMS, the voice over LTE IP network, and so on. And the tunnel endpoints are terminated in the PGW here. The user plane is happening here, and the control plane is happening at this level between the SGWC and the PGWC. And this so-called S5, S8 interface, that's the GTP-based or GTP2-based control plane interface here stays exactly the same. Also, the user plane here stays the same. The S5, S8 does no change. It's just that they both don't terminate in the same network element, but rather in two separate network elements with some additional signaling interface in between. And it's this SXB interface in the PGW and the SXA interface in the SGW. So why would one want to do that? The most obvious reason is to scale out the user plane. Of course, in classic 2G, 3G networks, the bandwidth is relatively limited. So you don't have to worry too much about scalability. But if you look at 4G, then of course the packet rates and even LTE advanced and so on and carrier aggregation, there's a lot of bandwidth from every subscriber or potentially from every subscriber in every cell and so on. So the amount of aggregate throughput that you see on those network elements, the SGW and the PGW, is of course quite high. And if you want to scale now with a split control plane user plane model, you can have one control plane instance that controls tens or dozens or hundreds of user plane instances to scale the throughput on the signaling plane. On the control plane, you don't need that kind of scalability because the number of signaling messages, of course, is still relatively low compared to the gigabytes and gigabytes of user plane data. Also, it is splitting those two elements allows an operator to decentralize the user plane architecture, meaning that in the classic core network architecture, you have the PGW in the core network, and let's say, for example, I'm let's assume a hypothetical German operator that maybe has its PGW in Frankfurt, and I'm currently in Berlin. Then all the user plane data goes from Berlin to Frankfurt, and then there it leaves the tunnel at the PGW, and it goes into the normal internet, and then it goes back to Berlin, for example, or wherever. What is the internet site IP address that I want to reach? And that, of course, introduces a lot of additional latency, and there's some applications where low latency is required. So in a control user plane separated 4G core network, one could now have a user plane function that's in Berlin. And when the session is being set up, the network could choose a user plane function that's closer to me and then basically break out my IP data directly in Berlin without going all the way to Frankfurt to decapsulate the packet and then send it back over the same bundle of fibers that goes between large cities on the carrier networks. So latency reduction, and you can do all of that without introducing any changes to other network elements. So whether or not your core network is CAPS enabled is completely transparent to all of the other network elements. It only affects the SGW and the PGW. There's no change to the MME. There's no change to any other network element involved. Full compatibility is just basically an implementation detail of how you implement those gateways. These new interfaces that we already saw in the diagram, SXA and SXB, are based on a new protocol. It's called PFCP, the Packet Forwarding Control Protocol, which runs on top of UDP, which runs on top of IP. The protocol is structurally very similar to GTP control plane, GTP v2c. So you have a small shared common header and then information elements next to it. It runs directly over UDP, so no SCTP, no other existing protocol for producing reliability or retransmission or anything like that. All of that needs to be handled inside the PFCP itself. Since there is a specification for that protocol, it means that you can, of course, at least in theory, combine equipment from different vendors, meaning you can have a control plane implementation from one supplier, and you can have user plane implementations from another or from multiple other vendors around. That definitely is useful, since again, for scalability, it might be that you add many more user plane instances than control plane instances over time as your bandwidth grows, and you can source different components there. This PFCP is specified in TS 29244 for those who want to look at the details. It's not specified in some kind of formal syntax, no ASN1, no open API, RESTful services, nothing of that sort. It's one of those classic protocols where you have a textual description of how the individual information elements and header fields and so on are encoded. Quite surprising that new protocols in 2017 get still specified that way. Yeah, I think it's because it's the same people who work with GGP all the time, and that's also designed that way. So the protocol stack for this protocol looks rather simple. I mean, we have basically something under IP, then we have UDP, and we have PFCP and UDP, and that's it. So no complicated deep stack. And then, as I said, PFCP itself needs to include provisions for retransmissions and acknowledgements and so on, since UDP, of course, is unreliable between those elements. So what kind of functions does CUPS cover? Logically, and how then these functions are somehow controlled using PFCP. On the one hand, we have so-called traffic detection. That means matching of packets based on some criteria. Then we have functions such as charging or usage monitoring. Of course, there's some kind of accounting in a packet gateway to be able to bill subscribers. There is the question of allocating tunnel endpoint identifiers and IP addresses dynamically. We have IP address allocation renewal release for the user equipment, meaning when the PDP context or the bearers are established, of course, IP addresses are allocated to the subscribers, and those need to be allocated. And then we have a lot of parts for controlling the user plane forwarding. I mean, the easiest and most obvious case is you just forward the traffic between the user interface and the packet data network, meaning internet in most cases, or the IMS core. But then there's some special cases where forwarding is also buffered, which is used in some scenarios when, for example, there's no radio access bearer to the specific UE, but you get some mobile terminated IP packets. Let's say there's a mobile terminated IMS call or something like that. Then first paging needs to be triggered, and a bearer needs to be established, a radio bearer, and that needs paging. So the downlink packets need to be buffered while the paging is running until the radio bearer is established, and then the buffers can be flushed. Likewise, there's some special case with an end marker, which is used during handover so that it's known when the last IP packet that is transferred still to the old cell has been forwarded to the new cell. So some of the concepts we see in the PFCP protocol is an association and a session. The association is an association between network elements. So we have a control plane instance and a user plane instance, and we might have any number of either of those two. And between each tuple of a control plane and a user plane element, there's now a PFCP association, which basically is some kind of state that makes those two nodes, two elements aware of each other, and which makes them aware of each other's capabilities, what kind of optional features they may support, what kind of load they may experience right now, and so on. And yeah, as I said, it's important to understand there's only one such association for each tuple of control plane and user plane function. So in a very simple lab-grade CUPS-enabled 4G core network, you would have one control plane instance for the SGW and for the PGW, and another user plane instance for each of those two, so 4 elements, but only 2 of them talk with each other. So you would have 2 associations, and that is exactly basically those that are symbolized here. So one association here and another association here. You only get multiple associations if you have multiple user plane instances or control plane instances that then spawn multiple like associations among those. This is association, and then on the other hand side we have sessions, and a session on PFCP exists at least for each tunnel, which means each bearer in the language of the 4G evolved packet core specs. You can even have more of those. We will have a look at these, but that is in general, you have one session for each of those tunnels, meaning that a normal, let's say, if you have a normal non-IMS LTE phone that is registered, you will have one session for each subscriber between the SGWC and the SGWU, and another PFCP session. So basically, for each subscriber, you have one session here, and you have another session here between those 2 elements. And if then you add IMS, you have additional sessions for the same subscriber on those interfaces. So you have 1 to multiple sessions for each subscriber in your network on both SXA and SXB. They are completely unrelated from each other. So the so-called node-related procedures then consist of association setup, update, and release. As that, basically making aware those individual network elements of each other and their capabilities and load. There's also a heartbeat procedure, which is basically just a keep alive to make sure that the other end is still there. Remember, we're talking about UDP, so if we don't have a heartbeat and we don't have any signaling traffic, we have no way of knowing if the other end is still alive. And that's why there is a heartbeat procedure, so they can check each other's availability status. On these session-related procedures, we now have basically 3 key procedures: session establishment, session modification, and session termination. Create, modify, delete, basically. And each of those sessions then consists of a potentially lengthy, in some cases also short, list of different rules. That's the concept that the CUPS designers and the CUPS spec have defined. We will look at those rules in a few seconds. So session establishment basically happens at the time when a bearer is established. So a phone registers to the network. This means a default bearer is established, meaning an IP address is allocated to the user equipment here on the left-hand side, the tunnel endpoint on the packet gateway, and so on. So all of the normal state in the core network is created, meaning there is a bearer, and then this means there's a session established here between control and user plane, and a session established here on those that side as well. The packet processing abstraction, as displayed in the CUPS specification, or even the PFCP one, I don't know which of the 2 specs it was, looks like this. It's actually not the best diagram from the specs. One should probably draw a better one. But in general, the idea is that in your user plane function, you have packets coming in and you have packets going out. By the way, the T is already cut off this diagram in the original 3GPP specification. So packets come in, then you look up some packet detection rules, the PDR. Packet detection rule is basically a packet filter matching on IP address, tunnel endpoint identifier, and possibly some other bits. And then once you have looked up your packet detection rule, the PDR then points to additional rules. And the only mandatory one, that's why there's a non-dashed box, is the FAR, the forwarding action rule, which defines what will happen to the packet if it has matched this specific packet detection rule. and then those instructions are applied, and the packet is forwarded. There's some other possibilities for other rules, and we will look at those in detail. But in general, first packet detection rule, then forward action rule, and probably or possibly some other rules that may apply in this data plane or user plane. Data path sometimes is also used in the network engineering. So how does a packet detection rule look like? It matches on any of those, possibly source interface, in which network interface did the packet arrive. What is the UE IP address, the inner IP address inside the tunnel? The fully qualified tunnel endpoint identifier, which basically means the IP address, port number, and TID. And then, in addition, optionally so-called SDF filters. That's session detection filter, I think, that is used in case you have multiple bearers. If you remember one of the IMS talks that I gave in IMS, there is one tunnel for all of IMS, meaning the SIP signaling and the user plane, the RTP flows. But and there's only one IP address and one tunnel for that. But within that tunnel, we have multiple bearers: the default bearer, the dedicated bearer for and the dedicated bearer for the voice plane. And those have different TE-IDs, and so packets might be filtered, for example, on port numbers. So you can have additional filters in here in this SDF. Then you can have a specification of outer header removal, meaning we should decapsulate outer headers. Outer header means basically the GTP user plane header that is there. And then we have pointers to further rules. We have at least one forward action rule pointer or identifier, basically, that points to such a rule. And we may have one or more usage reporting rules or QoS enforcing rules associated with that as well. And that describes all the packet processing for such a session. Now, after the PDR has matched, we look up the FAR, the forwarding action rule. And the forwarding action rule then contains information on what to do with the packet, including information to which destination interface, the network interface to which it shall be forwarded, whether or not we should create a new outer header and with what parameters, whether or not a session end marker is to be included in that header, some transport level marking. I haven't looked at it in the detail, but the name implies probably QoS bit settings on the IP header and so on. The policy, whether or not to forward or to buffer or something like that. Then there's the very fancy name, container for header enrichment. I really like that phrase. I mean, it's I've been working in packet processing and networking for more than 20 years now, but enrichment of headers is definitely a new terminology. So I haven't looked at what it does. We can look at it in case somebody has a question about it. And some additional stuff related to buffering that may or may not be there in the forward action rule. But at the very least, we have destination interface and forwarding policy and outer header creation in a typical forward action rule. Then if you look at other rules, there is usage reporting, for example, where you can configure. U means the control plane instance talking to a user plane instance. It can configure the kind of triggers and thresholds that should happen. So basically we can say, well, every such and such a period of time, there shall be a notification to the control plane. Or we can say, based on volume, every time a megabyte is consumed, there should be a notification, for example, or only at a fixed time, and so on. And there's also an inactivity detection possibility. So you could say, well, if there's no activity for a couple of minutes, the user plane function should report this to the control plane function, and then the control plane function can whatever tear the tunnel down or do whatever. I'm not sure why that is there. probably relates to some sophisticated billing models that people have around. Yeah, Domi is educating us about where header enrichment is used. But yeah, I said we can look at that later on. It sounds fishy to me. So a QoS enforcement rule, if it exists, it tells us what kind of packet rate or bit rate, guaranteed or maximum bit rate this session should be exposed to. That's how the traffic shaping basically works in the packet gateway for mobile subscribers. If you have a data plan that only allows you a certain bit rate, then that will be implemented by such a QoS enforcement rule. Basically, the information of your subscribed bit rates comes from the HSS to the PGW, possibly involvement of the PCRF there, and then the control plane instance can insert a QoS enforcement rule into the user plane instance, which then takes care of doing that. There's also buffering action rules. I didn't get around completing that slide, which basically just says how deep, how many packets should be buffered, and if buffering should happen, if buffering is configured at that time. Yeah, and that's really about it. You have those rules and sessions that get created, modified, and deleted. A bit of outlook on how CAPS and PFCP is used in 5G. In 5G, the PGWU, the user plane instance, becomes the UPF, the user plane function, and the control plane instance of the PGW becomes the session management function. So in a 5G core network, you would see those terminologies. Of course, everything inside 5G is a function. It's functional networking. And the protocol nicely remains PFCP. So you can have a user plane function that serves as a PGWU and as a user plane function, and you can have it used from 4G and from 5G core network side without any differences really, and or any modifications. It's still the same protocol and still the same technology. CAPS for 2G and 3G is not explicitly specified as far as I know, but of course anything that handles GTP user plane data can be modeled in this principle. So you can apply the same to an SGSN and to the GTSN, where as an internal implementation detail, the SGSN or the GTSN can offload the user plane processing to a user plane function. It's, as I said, it's completely transparent to anything around it. So, of course, one can implement those network elements this way. And I think maybe if you use OsmoGGSN with the Linux kernel GTP module, then already you have a control user plane split, even before that was even specified in 3GPP. It just wasn't called that way, and it doesn't use the PFCP between those two sites, but already you have the control plane curiously, you have the control plane in a user space process, and you have the user plane in the kernel driver, but you already have that functional split. So what we don't have is this PFCP protocol, but fundamentally it's the same idea. And we might see more of this in Osmocom in the future in our 2G, 3G implementations, where the GTP user plane handling is offloaded to a user plane function over PFCP. I think sooner or later, both on the SGSN and on the GTSN side, but that's for another talk. Now, what kind of open source software is there around this CAPS principle and PFCP yet? There's a number of different FOSS implementations around. Open5GS has C language implementations of the SMF, basically the control plane instance of CAPS, and the user plane function called UPF also in Open5GS, which is also a C language implementation just running purely in user land, meaning it's a normal application process using sockets API. certainly nothing that would perform very well or do a lot of bandwidth, be able to handle a lot of bandwidth. It's basically a simple implementation that's as generic and as portable as possible, but doesn't have a lot of performance. The ERGW or ERGW is an Erlang PGW and GGSN project that has been around for quite a number of years and is professionally deployed. The control plane is written in Erlang, and then they are using a user plane function that is based around Cisco vector packet processing, which uses DPDK to talk to the network cards. So using highly non-standard mechanisms to bypass all of the kernel networking stack and doing all the processing in there. There is another project called OMAC, which has actually two implementations, the NGIC RTC and the UPF EPC. It's the name of the Git repositories and the projects. So in the first one, they have they use a different framework on top of DPDK called BESS, the Berkeley something enhanced soft switch or something like that. I forgot the exact expansion of the acronym. Basically going the same route with DPDK, bypassing all of the kernel network stack. And the then updated version, this is more 5G EPC implementation, and that one, the UPF EPC, is 5G, so 4G and 5G versions of CUPS principle. And Free5GC also has CUPS with PFCP. They went yet another path by using a custom non-mainline Linux kernel module for GTP handling. They didn't bother to submit patches and extend the existing GTP kernel module. So you have to patch your kernel or at least run non-mainline kernel modules if you want to use their implementation. And soon we will also likely see an OsmoCom project that implements a basic user plane function, of course, with only very limited feature set initially. And the goal of this is to have no dependency on out-of-mainline kernel code. So still use all of the normal kernel stack, no DPDK, but still have something that is as fast as possible as you can get without basically leaving the standard Linux network stack. That means no, we will not be using normal socket-based read and write calls for every packet that we receive, but also do the actual packet handling in the kernel, but not by introducing additional non-mainline components that people that need to patch their kernels or install stuff that's not part of a normal Linux distribution. Yeah, and with that, we come to the end of file. That was my quick introduction into CUPS and PFCP. We can have a look at some PCAP files in case somebody is interested in that. So I've opened a PFCP. We can remove that part here. We don't want the hex dump. So this is a trace of a user equipment registering for internet and Welte services in an Open5GS installation. And I've added host name aliases to Wireshark so that we can see not the IP addresses, but we see some symbolic host names here translated. So we see here the SGWC communicating with the SGWU. That's the one session that gets created. And then we have the same between the SMF, which is basically the PGW control plane, and the UPF, which is the P2W user plane function. And let's look at that. For example, this create session establishment request from the control plane of the PGW to the user plane of the PGW. So we see it's a UDP packet on port 8805 on both ends. And then we see the PFCP header, which is relatively boring with a sequence number, a length field, and a message type, basically. And then we have various information elements. Most importantly, the create PDR, the packet detection rule that we want to create. Actually, multiple. It's the first one that we create. I hope it's large enough. If I should increase the font size, maybe we can do. Can I? No, I can. How was that? That way. So maybe that's more readable also in the recording. So we create a packet detection rule. It becomes or it gets an identifier 1 because it's the first one we create. There's some precedence in case you have multiple rules. You can determine the ordering of those rules. Then we have the matching criteria. So we see the source interface is called core. So basically the interface facing to the core network. We have a network instance internet. That means that's the APN that we are talking about in this context. And the user equipment IP address that has been allocated is this one for IPv4. So if a packet matches like this, we will execute or perform the forward action rule ID 1 and the QoS enforcement rule ID 1, which will be defined later on in this packet. So we can do a quick skip of some additional PDRs here and go directly to the forward action rule. So here we have the forward action rule ID 1 that is created, and it says apply action, and only one action is set. It's a bit mask which says forwarding. So whenever a packet matches the packet detection rule that we just saw above, we configure that packets shall be forwarded, and it shall be forwarded with the following parameters. One is the destination interface is access, which means basically the interface facing towards the SGW in this case. And we should create an outer header with the following information elements. That means we shall create a GTPU UDP IPv4 header with this tunnel endpoint identifier and this this IPv4 address. We probably skipped one important bit in the packet detection rule. No, it's fine. It's correct. Yeah. Of course. We don't remove any header here because the PGW, we get the native IP packet. There's no header removal in the packet detection rule, but in the forward action rule, we see an outer header creation. So basically it's an encapsulation rule for packets going that way. And if we look for the QoS enforcement rule that was created here, we get basically some uplink and downlink maximum bit rates that are specified and that originate from the configuration for this subscriber in the HSS, in the database of subscribers. Then there's a response to that, and the response basically just collects the rule identifiers. Basically, we have created this PDR, we've created some other PDRs, so all of these are confirmed and the request was accepted, so it's a full acknowledgement to all of those new PDRs. And that was basically it. That's the procedure that establishes the initial packet detection rules. We've seen there are multiple in those packets. So we have one create PDR, we have another create PDR, and yet another PDR, and then the forwarding action rules, and also multiple of those, and the QoS enforcement rule that we looked at. So if we look at the additional packet detection rules, the first packet detection rule was source interface core. So that's basically the mobile terminated traffic. And the second packet detection rule is source interface access. So that's the opposite direction. So we match on packets with a certain TID, tunnel endpoint identifier. On the access interface for the internet APN, and there we should remove the outer header. So we remove the GTP and UDP and IPv4 header from the packet, and then we execute the forwarding action rule dynamic by CP2. And if we look at that rule, we see the apply action is again forwarding. So uplink traffic should also be forwarded. And the parameters means the destination interface towards the core. There's no new header being pushed on it because, of course, an uplink packet that arrives GTP encapsulated gets decapsulated in the PGW and then leaves as a normal IP packet without the outer header on the public internet or whatever is the interface that we are connected to. Okay, that was sort of what I wanted to show. Thanks.